Okay, welcome everybody. It is my pleasure and honor to introduce our first keynote speaker, Professor Vivienne from MIT. She leads the Energy Efficient Multimedia Systems Research Group and is widely recognized for her work on energy efficient computing systems for machine learning, computer vision, and video processing for a wide range of applications, including autonomous navigation, digital health, and the Internet of Things. She has received many awards, including faculty awards from Google, Facebook, Qualcomm, and Best Paper awards from the Symposium on VLSI Circuits, the IEEE Custom Integrated Circuits Conference, as well as IEEE Micro Top Picks Awards. In addition, she has also received the Primetime Engineering Emmy Award for the development of the high efficiency video coding video compression standard. Vivienne has co-authored a book titled Efficient Processing of Deep Neural Networks, which I really love as an excellent introduction to the topic. Today, she's going to talk about efficient computing for AI and robotics, from hardware accelerators to algorithm design. A few housekeeping comments. You can post your questions in the chat, and I will read them out to Vivienne directly after her talk. We may not be able to handle all the questions in the limited time, and Vivienne has graciously agreed to be available for 15 minutes after this session in Gather Town, so you can go ahead and ask her questions in Gather Town itself. So let's welcome Vivienne and hear from her. Thank you.
Share with you some of the work that we've been doing in the area of efficient computing for broadly AI, and then also targeted at robotics applications. And in this talk, I'm going to cover some of the work we do from an accelerator perspective, and then lightly touch on some of the algorithmic design aspects as well. I should also note that this work is done in collaboration with lots of folks below. And also the slides are also available at this link here. So if you just want to follow along at your own pace, feel free to grab a copy there as well. Okay. So, you know, a lot of the exciting work in AI currently happens in the cloud, but there's a lot of compelling reasons to move it out of the cloud and into the edge, which is where we focus our research. One of the issues is we want to reduce our reliance on communication, especially if we want this technology to be deployed worldwide, where they don't have very robust, guaranteed robust communication infrastructures. Also, in a lot of applications related to AI these days, we're dealing with very sensitive or private type of data. And so rather than moving the data to the cloud, you might want to move the compute to the data itself. And then finally, when we're talking about interactive applications, and this is where robotics comes into play. So for example, in self-driving cars, latency is very critical. So you might not have enough time to send the data to the cloud, wait for it to be processed and to be sent back. So doing processing within the robot is very critical for low latency applications. Now, the main challenge, of course, of moving the computing out of the cloud and into the device or robot itself is going to be power consumption. So if you look at, you know, the amount of compute that's needed for, you know, autonomous vehicles, if you look at just general purpose computing or general purpose processor, you're talking about like thousands of watts in power consumption. And of course, this is going to be an even more significant issue as you shrink down the form factor, the size of the device itself, to something, let's say, that fits in the palm of your hand. So a smaller robot, or maybe your phone, right? And there in these handheld devices or portable devices, you have a limited amount of energy due to the size, weight, and weight of the battery itself. And existing processors tend to consume a lot more power for these applications than what we really can budget for these embedded applications, which is typically limited to under a watt due to things like heat dissipation, right? And since we're in a computer architecture seminar series, but you're all familiar with the slowdown of Moore's law and Dennard scaling, so we know that transistors are not becoming more efficient. And so as a result, we really need to look towards specialized hardware to achieve the significant improvements in speed and energy efficiency that we need for, you know, these high quality of result algorithms that are increasingly becoming more complex, and at the same time deliver the speed and energy consumption, energy efficiency needs of these particular systems. And from a high-level perspective, that's really the focus within our group. In addition to looking at new hardware, we really want to look across the entire stack. So we begin with looking at the algorithms themselves. Typically in the past, the algorithms for a lot of these applications primarily focus on quality of result. For example, high accuracy or high efficiency in terms of navigation path. But we want to jointly consider energy as well. So have a joint goal for the algorithm design and really start considering things like energy consumption and throughput or speed. We want to look at new computer architectures, thinking about things like the memory hierarchy and data movement across the memory hierarchy. We also build circuits within our group, so we often realize these new architectures into actual chips, and which we then integrate into actual systems as well. And so from a systems point of view, it's also important to think about not just the compute, but also the sensing and actuation power. Given the limited time, I won't go too much into the work that we've done here in systems, but if you're interested in that, I invite you just to visit our website. We've been looking at, for example, the balance of compute energy with sensing and compute energy with actuation. It should also be no surprise to the audience here that when we start thinking about, minimizing the energy consumption, what really dominates energy consumption is the data movement itself. And so this is a very popular plot from our cohorts showing that, memory reads from even small on-chip SRAM memory is going to consume more energy than multiplications or additions. And of course, reading from off-chip DRAM is even worse. So in general, the larger the memory and the further away it is, the more energy it's going to consume. And it can be orders of magnitude more energy consumption, consume orders of magnitude more energy than the compute itself or doing the operation itself. Now, when you combine this fact with the applications that we look at, is that the issue is that autonomous navigation requires a lot of data. Right. So for instance, one of the key things you want to do in autonomous navigation is understand your environment. In particular, you want to do what we call semantic understanding, where you can actually label each of the pixels so you can recognize that this is the ground, this is a person, this is the sky, and so on. Often you need to do this at high frame rates, particularly if you're moving quickly as a robot and your environment is changing. You might also need to do this at large resolutions in order to see objects that are far away. And then often you might need to also expand the data itself, for instance, to build like an image pyramid in order to see objects of different scale that might be necessary. And that's going to increase the amount of pixels that you need to process by 1 to 2 orders of magnitude. Another example of where we actually have a lot of data in autonomous navigation is when we want to do geometric understanding, which is to understand the locations of each object. Right? So for example, the depths of each pixels, and you might want to do this when you're trying to build a map of your environment. And you can imagine as you navigate for longer and longer, the size of the map will continue to grow. And again, that you end up having to manipulate a large set of data. All right, so these are the challenges that are posed to us with autonomous navigation. And so I'm going to kind of walk through some of the key blocks in autonomous navigation and talk about how we address these compute constraints. I'm going to start off with visual inertial localization. This is kind of the very first thing you want to do as a robot, which is to figure out where you are, right? So your location and also where are you actually looking at. And this is not just done in autonomous navigation, but also done in augmented reality and virtual reality as well. So you can imagine this, in those particular applications, the energy budget is very tight because you're talking about wearable devices. And so how it does this is it takes in a sequence of images, that's the visual part. And you might also, and this image is basically from a camera that's mounted on the robot itself. And it also might have an IMU on the robot. So you basically a gyroscope and accelerometer. And then you perform what we call visual inertial odometry, where you're basically fusing these two pieces of information, right? And so what you get is an output that kind of looks something on this right-hand side. So we're just displaying the camera input right now on the robot. And what you're trying to do is estimate your location and where you're looking at in the 3D space. And if you're navigating in an unknown environment, you might also need to create a 3D map. Some of you might be familiar with the term SLAM, simultaneous localization and mapping. So visual inertial localization is a subset of SLAM. It's just missing the loop closure itself. Okay, so one of the tasks that we charged our students was with looking at whether or not, looking at this kind of complex algorithm, which I won't go into too much details of, could we actually build an efficient chip that can do all that processing at an aggressively low power budget. So indeed we could. So one of the first chips that we built here, called Navion, is the first chip that does complete visual inertial odometry. And so it does a lot of the image processing, which is what we would consider like dense processing in terms of feature detection, and then it does some sparse processing of tracking the features across the different frames. So it processes basically the input of the camera feed. It also processes the input of the accelerometer and the gyroscope in the IMU. And then what it does is it takes these two modalities of the feed and it fuses it together with a back-end optimization with a pose graph, or you might refer to this as a factor graph. And this would be some form of sparse processing. And so these are all, all these components that we mentioned here are all shown here in the chip itself. So this chip is 4 millimeters by 5 millimeters. You can see that you could mount it on a small drone. And to no surprise, it's actually, orders of magnitude more energy efficient than mobile or desktop CPU. Now, the key thing that allows you to achieve the efficiency, in addition to the fact that it's specialized, is the fact that we really focus on reducing the amount of memory that is required, the amount of data movement that is used for this processing. Indeed, at 24 milliwatts, we're still able to achieve high frame rates between 28 and 171 frame rates. But overall, the only amount of memory we require and the data movement that we require is under a megabyte. So first of all, the key thing is that we want to integrate all of the processing for visual inertial odometry on the chip itself, right? Because we talked about how, going off chip to DRAM, for example, is very inefficient and energy costly. So it's important to integrate everything on chip. But once you integrate everything on chip, that's a huge amount of data, right? So how do you manage that as well? Because reading from large memory and moving that data around is also going to be very costly. So some of the things which lend itself more to kind of a co-design of algorithms in the hardware is we think about very lightweight approaches to compress the frame information as well. So often you have to store multiple frames to kind of track your previous frames and compare and see how the frames have changed. And so we introduced some low-cost frame compression. It's a block-based approach that we have introduced here, which doesn't affect the accuracy very much, but gives us significant reductions in terms of the storage cost. And then, as I mentioned briefly, on the back end, we often have to deal with graphical models and feature tracks. And so these are very sparse type of data. So we have to exploit sparsity here, both in terms of structured, in terms of the graph, and then unstructured in terms of the feature tracks itself, right? And so by doing all of this, we're able to significantly reduce the amount of storage that we have on chip to under a megabyte. So I didn't go too much into detail of this. If you're interested in this particular topic, I invite you to visit the Navion website, where we have a full-out video that goes into the details of each of these types of optimizations and how the algorithms work. What I want to move on to is actually focusing on understanding the environment. So once you figure out where you actually are, you want to look around to see and kind of maybe construct a map or understand what's around you. This can involve things like we said, depth estimation, where given an actual image, can you estimate the depth of each pixel? Or given an image, can you label the class of every pixel, which is known as semantic segmentation. This is a very critical operation these days in robotics, also known as perception. But of course, it should be no surprise to you guys that the state-of-the-art approaches to do this involve using neural networks or deep neural networks, which, as we know, requires several hundreds of millions, in this case, recently billions of operations and waits to do the computation. So it's extremely expensive. Just to give you a reference point, if you compare it to something that we all have, for example, on our, like on our cell phones, which is video compression, you're talking about at least 2 orders of magnitude increase in complexity. So it does pose a significant challenge if one day, for example, you'd like to have deep neural networks as ubiquitous as video compression out there. The complexity and the energy cost is quite significant. We also know that DNNs are used beyond robotics in many applications, but I won't need to go into this. And as Mark mentioned, Joel Emmer and myself, as well as some of our students, spent the past year and a half basically putting together a book on this particular topic. So I'm going to go through some of the key ideas in this particular topic that we've been working on, some principles that we've distilled. But if you're interested in taking a deeper dive, I invite you to check out this book. And I believe it's free to download for academic institutions, right? And for those of you who might not be familiar with, though I think most of you are, the kind of the key building block in the deep neural networks is some form of a weighted sum, followed by some nonlinear activation. And it's the, these MACs that really dominate or account for a significant amount of the computation, particularly when we're talking about processing images with convolutional neural nets. And convolutional neural nets, which is a specific type of DNN, basically involves these high dimensional convolutions where you apply a 3D filter to a 3D input feature map to generate, outputs. And the real challenge in terms of, processing these DNNs and CNNs and so on is first the dimension of these tensors or these filters, and also the fact that the shapes, and by shapes I mean like the height, width, and number of channels of the filters, input feature maps and output feature maps can change from layer to layer. So from a hardware perspective, that means that your hardware has to be flexible enough to support all these different filter shapes and input feature map different shapes, and also ideally be efficient across this range of different shapes. And of course, we know that in general, the filter shapes and the number of layers in these DNNs in general are getting larger and deeper. So there's more compute that's necessary. All right. Some quick things though that you can leverage in terms of looking at the DNN is that, as I mentioned, a lot of the operations are multiplies and accumulates. So high parallelism is actually possible, which high parallelism is there, so you can basically exploit that for high throughput. The main challenge, there should be no surprise, is the memory access bottleneck, right? So for every MAC or multiply and accumulate you do, you basically have 3 reads and 1 write. Right? And so, for example, if these came from DRAM, which you obviously would never try and do, you're talking about orders of magnitude increase in terms of comparing memory access cost to compute costs. And for example, in any net, we'll just take AlexNet as an example, for 700 million MACs, you're talking about 3 billion DRAM accesses. But there's also properties that we can leverage in DNNs. In particular, there's a lot of opportunities for what we call input data reuse. Up to 500x, for example, for AlexNet. What do we mean by this? For instance, if you're doing convolutional nets, you're applying a convolution between the filter and the input feature map. So the same weights and activations are going to be used just in different combinations throughout the slide as you slide the window across. Similarly, you often need to apply multiple filters to the same input feature map. So that means that each activation in the input feature map is going to be reused multiple times across the different filters. And then finally, if you're going to process multiple feature maps at the same time, then a given weight in the filter can be reused multiple times across the different inputs as well. So there's a lot of reuse opportunities. And then the key thing is to be able to exploit these reuse opportunities at very low cost memories. What do we mean by this? That means, having a small, let's say a 1 KB scratchpad memory in the ALU, or so in the processing element right beside the ALU where you're doing the processing, right? And if you have a very small memory there, the energy cost of reading from such a small memory is comparable to performing that multiply and accumulate 1x. Let's say you have a range of these PEs and they can talk to each other and share data, then getting data through the NOC from a different PE might be 2x the energy. Then you might have a shared global buffer, right? That might be a bit larger, from 100 to 500 KB would be 6x the energy. And of course, as we mentioned, going to DRAM is very expensive. And so the main challenge here is that how do I take this very large neural network, cut it into small pieces, and what is the order of the small pieces that I want to use to store in this register file so I can reuse it for as many operations as possible, and minimizing the amount of time that I need to go fetch from the next layer of the memory hierarchy, which is in some sense pretty standard in computer architecture. So as you all know, there's been a huge amount of work in this space. So one way to classify these different types of work is in terms of basically how they order the data as it goes through this memory hierarchy, which we call the data flow, right? So one type of work, one approach is basically what we call weight stationary. And the idea is that you want to store the weights of the neural network in that small register file within the memory so that the weight energy is significantly reduced. So the cost of reading that weight is very cheap. But the problem is the cost of the activations and the partial sums as you're doing the accumulation become much higher. So there's an emphasis of minimizing weight energy, but it comes with a trade-off of the partial sums and the activation. This is the type of data flow that you would find in the TPU and the NVDLA. Another strategy is to say that, hey, for the weights, I only read them. but for the partial sums, I do both reads and writes. So maybe it's better to store the partial sums in this local memory, and the partial sums accumulate to the output. So that's what we call this output stationary, whereas this is called the wait stationary. So basically the movement of the partial sums is significantly reduced, but this comes at a cost of data movement of the weights and the activations. And again, some other works also look at using this output stationary flow. In our own work, in the IRIS work, we looked at what we called a row stationary flow, which is that the main key thing is you don't want to focus just on the weights or just on the partial sums, but we want to do a balance of both. So the idea here was that you process one particular row, or you slice up your neural network so that you're processing one row at a given time within the processing element. And so within this processing element, you're able to leverage convolutional reuse between the filter and the feature map, and also maximize the row partial sum accumulation in the register file. I won't go too much into details about this because we have lots to cover, but this is something if you're interested in to go visit the ICCAD paper. But the idea here is that this is one row, we can expand it into multiple rows because obviously a DNN itself is very high dimensional, right? And so basically each of these columns of PEs are basically computing one output row, and then you can have multiple columns to generate multiple output rows. The key takeaway from this though is that basically rather than favoring one particular data type, what the row stationary data flow allows you to do is kind of balance the different data types and very much optimize for the overall energy efficiency as opposed to the energy efficiency of one particular data type. And objectively that seems like it makes sense, right? It's always good to optimize for the right objective here, which is energy efficiency, as opposed to just the data movement of one particular data type. And this is reflected in terms of looking at the energy breakdowns of these different data flows. So for example, here in the wait stationary case, right, we can see that the wait energy shown here in green is really minimized, but it comes at a cost of a lot of energy for the partial sums and the activations. Whereas output stationary, when we look at 3 variants of it, really minimize the partial sums. So you can see that the red part here is really minimized, but it comes at the cost of increasing the weight and activations. Whereas row stationary, shown here, it doesn't have the smallest amount of weight energy or the smallest amount of partial sums energy, but overall, when you put it all together, it still has the best overall energy efficiency. Okay, so again, the takeaway here is that you want to always look at, for example, if you're talking about data movement, all the different data movements, not just one particular data type, and you might need to balance them out. So in order to kind of demonstrate that this data flow can actually work in practice, so we built a chip called IRIS to demonstrate the row stationary data flow. This was published at ICCAD back in 2016. And really what we want to show is with an array of 168 PEs, we want to show that we can have a very efficient data flow, and it also could be reconfigurable to support the different layer shapes, right? And with the row stationary data flow, we're able to reduce the amount of memory access from the shared global buffer by 100x and reduce the amount of off-chip data access by 3 orders of magnitude. And at the time when we compared it to NVIDIA's TK1, which was in a 28 nanometer, this is in a 65 nanometer process, you are over an order of magnitude more energy efficient, right? And these, again, we have this whole IRIS website that goes into this in much more detail, and this is in collaboration with Joel Emmer. Okay, so I mean, this seems great. We also had some, this work also exploits some sparsity, which I won't get too much into. But if you take a step back and just think from kind of a systems point of view. So if my objective is to build an efficient system that can be energy efficient and achieve high accuracy, what I really care about is just the energy versus accuracy trade-off, for instance. And I actually don't really care about what the underlying hardware or algorithm is. Just give me the energy versus accuracy trade-off. So this is what we've shown here. So on the x-axis, we're looking at accuracy, and so this is on a linear scale. And you can see that when we compare DNN-based approaches, and now I would say it's even higher, compared to handcrafted based approaches. So HOG is a histogram of oriented gradient. This was basically what was considered state-of-the-art before this whole resurgence of DNNs in around 2012. And if you compare the accuracy for, this is an object detection task of AlexNet and VGG compared to HOG, indeed, DNNs are giving you double, if not almost triple the accuracy. So the higher, the better here. So that's great. But the real interesting thing is if you look on the y-axis, which is the energy consumed per pixel, and this is on an exponential scale. And so as it turned out, during that time, we had 2 PhD students in my group working on these various different approaches of doing object detection. So we had one student, Yushin Chen, working on a DNN-based approach, which is the iris work that we saw. And then another student, Amar Soliman, looking at, these handcrafted feature-based approaches. How can you build efficient hardware to do those? And so they basically, started design and taped out the chip at the same time. These are same, process technologies, same area. And so these numbers are measured numbers from these, dedicated silicon. And what you can see here is that using histogram of oriented gradients, though its accuracy is lower than AlexNet and VGG, its energy is quite low. It's actually below a nanojoule per pixel. And as a reference point, video compression is typically around a nanojoule per pixel. So what's really impressive here is that for the same energy you would have spent on compressing the pixel, you can actually understand the pixels, right? Maybe not super accurately, but accurately enough, right? As you go to more sophisticated algorithms, at the time looking at AlexNet and VGG, certainly, as I mentioned, you get double or maybe even almost triple the accuracy, but the energy grows significantly, right? So here we're talking about 2 orders of magnitude difference in energy consumption from AlexNet versus HOG, and then over 3 orders, almost 4 orders of magnitude increase from VGG compared to HOG. So one question you might want to ask yourself is, though we're also, super excited about the accuracy of deep learning, would you be willing to pay? So for example, if I said on your phone, I'm going to double the accuracy of, the processing that's going on for recognition on your phone, but your battery life is going to, die 300 times faster. Is that a particular system that you're interested in, or even 10,000 times faster, right? So clearly the energy cost really should be further us, and this is already, I should mention, with specialized hardware. So really more needs to be done to bring this energy down while still maintaining accuracy. And so as it turns out, there's been a significant amount of work in looking at doing precisely this. So not just looking at algorithms as though they're fixed workloads, but how do we change the DNN algorithms to make them more hardware friendly? So the joint design of algorithms and hardware really, again, to pull down this energy cost, because just going to specialized hardware is not enough. We need to, further reduce the energy cost. And so we spent quite some time doing kind of surveys of these areas. So some of you may have attended the ICCAD tutorial that we held. This was with Jill Emmer. And we put together proceedings papers. And so exploring a lot of the work that we've been looking at, or people have been working on this space, we actually identified various limitations of the existing approaches. So I'll share with you some of them. So the first thing is, okay, let's look at a little bit from the algorithmic side of things first. So there's various different approaches that people are using to try and make these DNN workloads potentially more efficient. One popular approach is what we call network pruning, which is basically setting some of the weights to 0. And then we know that anything multiplied by 0 is going to be 0. You can skip those operations, and also you can reduce the storage cost of the weights. Another thing is to take these, large filters that we were talking about, these 3D filters, and then decompose them into, for example, 2D filters. So depth-wise layer and point-wise layer. Here you'd have fewer operations and potentially less storage as well. And then also there's been a lot of work on reducing precision, not using 32-bit float, but going down to 8-bit and even, binary or 1-bit precision. Now, a lot of this work focuses on reducing the number of max and weights, right? And that's because it's easy to compute given the DNN workload. But really, from a systems point of view and a hardware point of view, what we actually care about is, does this actually translate into energy savings and reduce latency? Because those are the actual metrics that we care about when we're building the system. And so the challenge is that unfortunately it doesn't directly translate. So you can't just look at the number of max and weights as proxies for energy cost and latency. So I'll give you some examples why. So this is a plot that was from Google's mobile vision team, and they're showing max versus latency. And you can see here that for a given number of max, you can have a 2x swing in terms of latency, and for a given latency, you can have a 3x swing in terms of max, right? And this is because, depending on the shape of the DNN, it might not map as well to your array of processors, so utilization can vary depending on the shape of your DNN. And so the conclusion for this is that You can't, the number of operations does not alone approximate the latency well. You can't just look at number of max and be like, oh, this is how quickly it's going to run. It really depends on how it maps onto your hardware. Another thing is looking at weights alone. So counting this, look at the size of your DNN. Is that a good metric for energy? And so in our own research, we looked a little bit into this, and other people have looked into this as well. And again, it should be no surprise to you, based on what we've talked about before, which is that, there's multiple types of data in a DNN. It's not just the weights that move around, it's also the feature map activations that move around as well, right? So all data, the data movement of all data types should be considered when evaluating the DNN, the energy of the DNN. And also, it's not just, all weights and all activations are not created equal. It depends on whether or not you're which level of the memory hierarchy you're reading them from. Do you have a lot of reuse for those weights, right? So if you have a lot of reuse, maybe the cost is less. So it's not as simple as though it's really easy to use max and weights as maybe a 0th order estimate of complexity. When we start looking at real hardware metrics like latency and energy consumption, it's really important to look a bit deeper, right? And so some of our work in the algorithmic space is to think about how can we actually incorporate these, what we call hardware metrics like energy and latency, into the design and the optimization of the DNN itself. So for instance, in the task of pruning, which is removing those weights and setting them to 0, rather than in the past, people focused on removing weights that are small based on the magnitude of the weight. You might get 2x, but if you can actually remove the weights that consume the most energy or based on their energy consumption, factor that into the design, then you can actually achieve much more energy savings. And this is for the same accuracy, right? So one way that we approached this was we sorted the layers based on the energy consumption, and then we started pruning the layers that consume the most energy first, because likelihood is that those weights would consume more energy, and then as we mentioned, you get about a 1.7x improvement in energy savings. This is, again, the idea here is that you want to minimize energy, so you should directly target it in the algorithm itself. Another example is some work we did with Google's mobile vision team, which was inspired by the energy aware pruning. And the idea here is, can we optimize this whole process? And rather than just pruning individual weights, prune channels, or basically discover the network architecture based on empirical measurements from mobile platforms. Because for them, what they wanted to do was they, without knowing the details of the platform itself, whether the architecture or whatever framework it's using, can they plug it into a system where it takes empirical measurements of the latency and or energy and uses that to drive a neural architecture search algorithm called NetAdapt. And basically what NetAdapt is doing is it's given a budget, like in terms of latency and energy metrics, it generates a bunch of, it takes in a pre-trained network, that's the accuracy that you want. All right, it generates a bunch of proposals about how you can manipulate the network architecture here, for example, reducing the number of channels to hit this budget. And then it checks which one has the best accuracy, and it iterates until it gets an adaptive network that has a good trade-off between accuracy and latency, or accuracy and energy, a combination of that, right? And by doing this, when you compare it with, if you do this on MobileNet, which is already a very compact network, if you compare it with similarly handcrafted network architectures, you get 1.7x speed up for the same accuracy. And so the whole idea here is this is another mechanism by which we want to incorporate latency or energy directly into the optimization of the DNN itself. And here in this particular case, you don't need to know the details of the hardware to do this. Often a lot of these algorithmic works primarily focus on the task of what we call image classification, which is I give you an image and you're going to tell me one of, in the case of ImageNet, one of 1,000 classes that belongs to. So it's really simply reducing the information from an array of pixels down to one label. What we were interested in the robotics space, though, is a more challenging task, which is, for instance, given an RGB array of images. So this is just, it's just a regular snapshot for each pixel. Can I predict the depth? So here I'm not actually reducing the amount of information, but I'm actually kind of revealing more information per pixel. And the question is, because this task tends to have to retain more information, can these techniques that we just talked about in terms of optimizing the DNN for efficiency still work? So for this depth estimation task, we're indeed able to show that it does work. We apply things like NetAdapt and some neural architecture optimizations to get it to work, right? And so this is so just some measurements showing frames per second, so that's speed on the x-axis on a TX2 GPU. And on the vertical axis, it's the delta 1 accuracy. Delta 1 accuracy means the percentage of pixels that are within 25% of the correct depth. And you can see this work shown here in red is, order of magnitude faster than comparable approaches. And so we had similar accuracy. This work was actually presented at a robotics conference last year, and we actually want to show that it could run real time on an iPhone as well. So this is some video that we collected at ICCAD'21, and it can run at 40 frames per second. And so the code for this is all available on the FastStep website. Okay, so that's the algorithm side. Let's turn back to the hardware side of things. So it's great that all these algorithm folks are doing all these different things to make the algorithms more efficient. But from a hardware point of view, if you think about it, it actually makes things a little bit more challenging because we don't actually, unless you own the full stack, unless you can control what the algorithm person's going to do, what this means from a hardware perspective is that now you need much more flexible hardware, because if you want to be able to support and get the benefits of these approaches, you need to ensure that your hardware can actually exploit them. So I'll give you one example of where this is a challenge. So in particular, if we look at majority of the existing DNN architectures, they often rely on certain properties of the DNN in order to achieve high energy efficiency. So for instance, we often have an array of multiply and accumulate elements, right? And then because we know data movement's expensive, whenever you read a weight once from the weight memory, you're going to reuse it multiple times across the array. Similarly for the activation, you read it once and reuse it multiple times. Now the is, regardless of how you structure the MAC array, whether you're exploring spatial accumulation, like with weight stationary approaches, or temporal accumulation with output stationary approaches, the amount of reuse that you're able to exploit depends on the number of channels, the feature map, and batch size. And typically they're quite fixed depending on which type of data flow, for instance, that you're actually using, right? So for example, in spatial accumulation for weight stationary, you're reliant on the number of input channels and the number of output channels. For temporal accumulation, you're reliant on size of the feature map or batch size and number of filters. And so this is going to be a problem. We start thinking about the fact that the algorithm folks have started to make the DNNs much more compact, right? So for example, they look at depth-wise layer where you decompose that 3D filter into 2D filters, and in which case the number of channels you might have is reduced to only one, for instance. And so there's not much reuse in that input direction. And if your hardware is designed specifically to look for reuse in that direction, you're going to be inefficient, both in terms of reuse and also array utilization. This is also going to be an issue as you scale up. For scalability, as you scale up the array size, the utilization is going to drop even more, and it might be also challenging to exploit sparsity. Right. So some things that you need to do in order to address this is you need to have a much more flexible data flow and mapping so that basically you can exploit reuse in any dimension of the DNN, not just those fixed dimensions. And so it turns out row stationary with Iris does allow for you to search and find a better dimension to exploit reuse from. Another important aspect is the on-chip network. So when you're delivering data from your global buffer to the PEs, it really needs to be flexible in order to support these different things. So for example, if we look at, if there's a lot of reuse available, so if you talk about these large tensors or large filters that we have, you want to be able to exploit data reuse for high energy efficiency and high array utilization. So in this spectrum of NOCs, you want to lean towards more the right-hand side, where you can have low bandwidth from your global buffer, you read once, but then you reuse it multiple times in terms of a broadcast across all of these processing elements. So you have high spatial reuse. On the flip side, if we start having these things like depth-wise layers and fully connected layers, there's not that much reuse. And so there, if we want to have high utilization, we have to lean towards more on the left-hand side with unicast, where you have high global bandwidth from your global buffer, and you want to deliver, you need to deliver unique values to each of the PEs in order to keep them busy. And so, one solution for this would be an all-to-all network, but that's obviously too expensive and not very scalable. So that was really one of the focuses of the second version of Iris, which is like, can we come up with a NOC that is much more flexible? So we ended up looking at a hierarchical mesh, right? Basically what this is at the low level, we have these small clusters of all-to-all NOCs, and then these small clusters of all-to-all NOCs are going to be connected to each other through, at the next level, through a mesh router. So the mesh A mesh network basically allows it to scale, while the all-to-all connection gives it its flexibility. And so with this, you're able to do all the data delivery patterns that you really care about to satisfy all those different filter shapes and still have high utilization of your arrays. So if there is reuse, you can exploit reuse. If there isn't, you can still have high array utilization, right? And so as I mentioned, that's kind of the key, one of the key core elements to the second version of Iris. You're really looking at balancing flexibility and efficiency. And so you can support a wide range of filter shapes. We're just showing here the speed up here for MobileNet, which has different filter shapes, different layers. And also, we don't have too much time to talk about it, but also a wide range of sparsity. Because again, from a hardware perspective, you don't have much control in terms of how sparse the network is going to be. So in the case that you are trying to exploit sparsity, you don't want to introduce too much overhead if the sparsity is low. We also, because of the mesh aspect, we can actually scale up the architecture quite well. As we increase the number of PEs, the throughput also scales well, especially over the first version of Iris. So overall, we get an order of magnitude faster and more energy efficiency compared to the first version of Iris, because we've introduced this flexibility for more efficient, for a more diverse set of filter shapes, and also because we can exploit sparsity efficiently. Another piece of work that we looked at is how to, develop tools in order to evaluate the range of DNN accelerators out there. Is there a more systematic way that we can compare and evaluate all those different exciting architectures that exist? And if there's a systematic way of evaluating them, can we also, within that framework, rapidly explore the design space? So this is, again, some work we did with Joel Emmer and also the team at NVIDIA. And so it has two components. One is the Accelerators energy estimation tool. This is also inspired by a lot of the kind of CPU and GPU energy estimation tools that exist out there, except this is primarily for accelerators, so it has a lot more flexibility. And it's an early stage energy estimation tool at the architecture level. So basically you can define things like number of PEs, memory size, on-chip network, and so on. And then based on that, you can estimate what the energy cost will be. That will be the description that you push in. One aspect that makes it super flexible is these plugins that allow you to support different technologies and different properties of the components that you will use to build up your architecture. And I'll get a little bit more details into that later. And so as I mentioned, Accelerators is broadly for any type of accelerator, but you can combine it with something like Time Loop, which is a DNN mapping tool for you to actually profile specifically DNN accelerators. So the Time Loop itself will search the mapping space and will generate action counts from a performance simulator. And so with the action counts and then the architecture description and then the energy plugins, you can then generate the energy estimation itself. Of course, any energy estimation tool is only as useful as it is accurate. So we validated it on the Iris chip. In particular, we compared it to the post-layout simulations, and it was within 95% of the energy estimates. And indeed, it also gives you a lot of fine-grained aspects that allows you to break down not just the overall energy is the same, but you can see that the energy of the P array, and actually you can even see the energy of each specific processing element within the array itself. So it can capture all of that. Okay, so in the interest of time, I'll just go a little bit fast over this part, but in the infrastructure as follows. As I mentioned, you have an architecture description that goes into Accelerators. Actually, it's a kind of a hierarchical system. So for each of these components, you might have what we call a compound component descriptor. So for a global buffer, you might have SRAM and the address controllers. Processing elements have multipliers and adders. And then for each of these components, you might have an energy plugin that will describe the component itself in terms of the energy cost, right? So given the width, given this action, this is the energy cost. You might get energy counts from, action counts from the simulator, and then the output would be the energy estimation itself. And so what I want to highlight in Accelerators is that it has the flexibility in the plugin to actually not just, for a multiplier, say the action is multiply, but to capture much more fine-grained actions. So for instance, we know that a typical thing that we want to exploit in DNNs is sparsity, because anything multiplied by 0 is 0. So you want your multiplier to be able to capture those range of actions, not just that every multiply consumes the same amount of energy, but if you can skip the multiplication, it's a gated multiply, it's less energy, or if you can reuse some of the data of the multiply itself, one of the outputs doesn't move, then the energy is also less, right? So there are ways that you can have, with this fine-grained action, better capture the energy cost. And this basically allows us to capture a more detailed breakdown in terms of, for instance, the energy consumed per PE, because each PE might experience different degrees of sparsity. And this allows us to closely track the ground truth, which is the place and route simulations, without actually having to go, all the way to RTL of the entire system itself. Right, so we believe that having this amount of flexibility allows you to accurately capture and evaluate different optimizations in the DNN space. Another exciting area in the DNN space is in-memory computing. So the whole idea was that data movement's expensive, so why not move the compute into the memory itself, which is storing the weights. Basically, can you do the computation with the memory storage element, which might be, for example, a memristor, where basically this is going to be analog computation. For instance, the conductance of the resistor is your weight. On one side, you might apply a voltage, which is proportional to your activation value. And then because of Ohm's law, you generate a current, so it already does the multiplication. And then because of Kirchhoff's current law, you're going to accumulate the current, then that's a free addition itself. So this is all an analog compute. It's great, but has some challenges. It's very sensitive to non-ideality. So if there's some slight change in the memristors, you're going to be sensitive to that. And also, you often don't do everything in the analog domain, so you have to move between analog and digital. So you're going to have some conversion overhead there. And so a lot of this work leverages emerging memory device technology. Okay, so for the interest of time, I'm just going to skip this, but this is basically how we do memory computing. There's various different benefits. Go forward. What I want to emphasize is that Accelergy can easily support this type of technology. In fact, all you really have to do is change certain compound components and also maybe swap in new information from in your energy estimation plugin. So you don't have to, for example, if you don't change the architecture, you don't have to change the action counts, right? So basically, it's very flexible and allow you to explore different technologies. One of the hopes for this is this will help us bridge a lot of the research that's going on at the circuits and device level. A lot of people are looking at new device technologies, and this will allow them to explore from an architecture standpoint, what are the implications of those new devices. And again, Accelergy, we just showed that you can be accurate enough to capture that. Again, we ran a tutorial at ICCAD and also ISPAS this year of Accelergy and time loop. So if you're interested in this, I invite you to check this out some more. All right, so I also won't get into too much of this, but the main takeaway from this slide was just talking about, we had talked about the co-design of algorithms and hardware together. And so actually how you might design a DNN for in-memory computing is actually different from how you would design it for a digital processor. Because first of all, you have to be more resilient to noise or non-idealities in the devices. And so something that might have been, super accurate with no noise can actually drop quite quickly. And the other thing is that because you need to go from analog to digital and digital to analog, that cost of conversion can be quite high. And so often in memory computing, you want to have these very large arrays to amortize that cost. But then as we talked about, there's a lot of people building very, very compact networks. And so the utilization of these arrays are going to be a bit of a challenge. So in the book itself, we actually have a whole chapter discussing in-memory computing and all the different design considerations that you might want to think about as you're designing in-memory computing, because to deal with a lot of the challenges in that space. And often these might eat into the achievable gains compared to conventional digital architecture. So if you're interested in this topic, I invite you to check this out. All right, so I want to end my talk talking a little bit about going back to robotics. There was a lot about DNNs, but let's say, after you figured out where you are, you want to actually figure out where you want to go next. So let me restart this. So let's say you're a robot, you're trying to explore a completely unknown environment, and you have this depth sensor that you're scanning, and you're building this map. So the white part is stuff that is unoccupied, and gray part is unknown, and then the black part is a wall, right? So you're trying to build this map, and basically what you're trying to do is trying to go to the place where it hasn't been explored before, so you can get more information about the map. And so the question is how to do this quickly, especially if you can imagine something like a search and rescue type of thing you want to explore as quick as possible. There's many ways to do robot exploration, but a principled way of doing it is to basically formulate the problem in terms of a mutual information problem, or particularly Shannon's mutual information problem, right? So given a map that you already have, this is a probabilistic map because you scanned it with sensors that are a little bit noisy, where should you go next to do a depth scan to look at obstacles to get the most information given what you already know beforehand? One way to do that is compute the mutual information, which is a way to measure how much new information you could get depending on which region you go. And then you would actually go there and then scan and update the map, right? And then so shown here is a video of an actual toy car that we have in our lab. This is work with Surtesh Karaman, who is a roboticist, looking at, having a race car here, trying to go to the places where there's the most mutual information and to kind of search the map itself. Now, the interesting thing about this mutual information computation is that basically it's a simple summation, but the most important thing is that it's embarrassingly parallel. So it's very similar to DNN in that sense, right? So lots of things can be computed in parallel. In particular, often what happens is at a given location, you have these different depth beams that you're scanning in different diagonals, and you're trying to compute the mutual information. So the amount of information that each of these beams will, or these sensor beams will add to that given position. Okay, and so actually each of these beams, you can process those all in parallel, right? And then you would just accumulate the values. So like, okay, so, the beam 1 is gonna give me this information, beam 2, or beam 1, beam 2, so on. And so basically what you can do is you can assign the beam calculation, this summation for each of these beams to different processing elements, and they can run in parallel, and then they just add their results. So it seems pretty easy to parallelize. But again, the main challenge is going to be the data delivery, right? So you only have one map to read the intersection of, your probabilistic map and these beams on. And, in general, in SRAM, we typically are limited to 2 ports. Otherwise, the energy increases significantly. So you have 2 ports reading from the same memory, but you have multiple ports trying to do that. And so, of course, there's going to be a bandwidth limited issue. So the obvious solution is that you should bank the memory, right? So we're gonna break into B banks, and then you're gonna have to have some arbiter so you're gonna bank it in such a way that you minimize conflicts between each of these diagonal reads, and then you have an arbiter to resolve, if there are any conflicts, how to resolve that quickly. I'm just gonna focus on the memory banking pattern in the interest of time. So the question is, given this map, how should I break it up into different banks, right? So let's look kind of closely at the memory access pattern, right? So if my robot is here, I have these diagonal beams scanning out on this kind of grid-like structure, right? And so the numbers here denote basically the order in which the scans kind of go out across the different PEs. And basically what you'll notice here is that during every cycle, the PEs access the map locations in the same columns and rows. So there's gonna be some conflicts, right? So for example, the number 6 appears across these. So how can I break up this map to minimize the amount of collisions? And the other challenge here is that this pattern, however I break up this map into different banks, it has to be sufficient regardless of where I am on the map. So for example, if I'm in location A, I might be accessing it, with this radial pattern, and location B, I'm going to access in the other radial pattern. And whatever kind of banking pattern I pick, I need to ensure that I minimize conflicts for all these kind of access patterns. One naive way of approaching this would be to use, for example, vertical banking. So let's say each column belongs to a different bank, right? The challenge here, of course, is that let's say it's a 2-port memory. So in this case, looking at cycle 5, there's no conflict here. I can access these 2, but I will have conflicts when I access these 3 because they're going to be on the same column, meaning they're from the same bank. So one solution that we did was to look at diagonal banking, and in fact, diagonal banking does solve part of this problem. You can see that within each color, a given number only appears twice, meaning that I'm only accessing it with the 2 ports, and there's minimal conflicts there. So there's no read conflicts across the banks. And when we look at this banking pattern compared to vertical, so okay, this is the number of processing elements, and this is the throughput, and then the dotted line is the unlimited bandwidth scenario. If I did vertical banking, we can see that after a certain point, as I increase the number of PEs, I'm going to be bandwidth limited, so you're not going to get any more throughput improvement. But if you do diagonal banking and then you do some optimization with packing, you can get pretty close to the optimal throughput, assuming you within 94% of unlimited throughput, unlimited bandwidth. And then as a result of doing this, you can actually compute an entire map, quite a large map, 20 meters by 20 meters in under a second on an FPGA. So this is very different from before. What people had to do was they had to sample certain locations on the map and compute the mutual information there. But here, if you can compute the mutual information of the entire map, you can really determine the best the actual, global best place to go to get the most amount of information itself. And so this is kind of the first work that can facilitate that kind of decision making for robot exploration. After this work, we actually found a whole class of banking patterns that can actually satisfy these conditions. Actually, they're called the Latin square banking patterns. So you actually have these tiles where basically in each tile, the cells and columns are assigned to different banks. Sorry, the columns and rows are assigned to different banks. You'll see that like within a given column, we never have the same bank, and then you can tile them at a higher level. And so in our more recent work, we've rigorously proved that this basically minimizes the read conflicts for such an access pattern. And Peter, the student who worked on this, presented this at the student research competition, ACM student research competition. All right, so that was a lot of information, but at the very high level, the takeaway is that efficient computing is really critical for advancing the progress of both AI and autonomous robots. And so it's really critical for making these types of applications ubiquitous, regardless of the system size. And to meet these demands, again, the key focus on a lot of these applications is really looking at reducing data movements, coming up with new hardware that focuses making data a priority and reducing data movement. But also in order to do this, often requires the co-design of both the algorithms and the hardware. So not looking at, at fixed workloads and really trying to minimize data movement, but can we change the workloads themselves while maintaining accuracy? So there's this co-design of AI algorithms and hardware for AI and robotics to really focus on minimizing data movement together while maintaining the same quality of result. Of course, a lot of this work could not be done without the students who do great work, and my collaborators Joel Emmer and Surtesh Karaman and our sponsors. I didn't have too much time to go into the details of a lot of the work we do in the robotics space, but if you're interested in that, I invite you to visit our low energy autonomy navigation website, which is I jointly run this group with Surtesh Karaman, who's a roboticist. As Mark mentioned at the beginning, we also have this book. If you want to go even deeper into DNNs, I invite you to check out this book. It's 340 pages, so we'll keep you busy, and various materials are on our website as well, excerpts if you can't access the book, but as I mentioned, educational institutions can access the book mostly. And then we have, if you want to again do deep dive in robotics and or DNN lectures, we have a whole series of lectures on our tutorial page and our YouTube channel.
Okay, thanks a lot, Vivienne, for that excellent keynote. I guess we have time for just one or two questions. So there is a question from Oyon Ray. What are your views of about training at the edge? Because the hardware, a dedicated hardware might not be able to keep up with the evolution of the algorithms.
Yeah, that's a great question. I think, well, just the high level, even if it was just inference, there's always going to be this challenge of having the hardware be flexible enough to support whatever the topology of neural network is going to be, and also whatever additional new operations will come into play. So I think one of them, when I talked about the second version of Iris, was trying to balance at least the data from a data flow aspect, how to make it, and from the knock aspect, more flexible. But certainly that's going to be a challenge regardless of whether or not it is inference or training. And there's always going to be a trade-off between flexibility and efficiency. When it comes to training at the edge, I think the additional challenge is that certainly there's going to be issues of, let's say, storing the activations, which you didn't typically have to do before for the back propagation, and also challenges having to do with the compute precision. So typically you can't drop down to 8-bit or 1-bit, like the types of things that we're seeing for inference. So for training, you typically do need higher precision. Now, of course, there's research going on. I think IBM has done some really amazing research looking at, really trying to reduce the precision of training. So I think by default right now, like you have like brain float, or basically 16-bit floating point, I think is what Google is using and many other people are doing. IBM was able to show down to 4-bit. in a recent NeurIPS paper. But I think that's still an open area of research. I think the other question you should ask about training on the edge is from an applications point of view. So one question you should ask is, where is the labeled data coming from, right? So typically these days, a lot of the algorithms that perform really well in practice tend to be supervised learning, and that requires a lot of labeled data that's available in the cloud. But when you put things on the edge, then the question is, where is that feedback mechanism coming from? So it really impacts, the application really impacts whether or not you can do this.
Thank you. I guess there is a follow-up question from Sheetal. It's about Iris, whether it supports only convolutional neural networks, or does it extend to other neural network topologies as well?
Right, that's another great question. So Iris itself does support a range of convolutional neural network, convolutional layers and fully connected layers. You could view fully connected layers as basically being able to support matrix multiplication. So in that sense, it can support that. But I would say that when you start looking at things like transformers, which use matrix multiplications for the attention, but there's other types of processing. So certainly there would require some extensions for that. That might not be in the core data flow part, but some other kind of smaller operations that are related to that.
Okay, thank you, Vivienne. It's exactly the hour and our technical program is also starting, but thank you very much for the keynote. And if you could please move over and join us in the gathered space. I think we have the link over there. So Ivan, for example, had a question, and we could ask those questions to you in gathered.